Okay, so let's continue the case. So uh, we can use the Gauss-Jordan elimination to get the unit matrix, to change the coefficient matrix to be the unit matrix. Okay, and then we can go back to check the constraint equations. So let's say that's the C matrix U equal to, okay, sum the known values. For the previous problems, we can say that's the zeros, okay. And that's the constraint equations. If we change the constraint equations to the matrix form, then we can get the equation of this one. For the previous example problems, it could be a 2 by 6, or it could be a 2 by 15. This one is 6 by 1, 15 by 1. Or then this is a 2 by 1. Okay, so that's the constraint equations, and we know all the elements in the C matrix. Also, we know all the elements in the right-hand side vectors. Okay, so if we do the Gauss-Jordan matrix, if we apply the Gauss-Jordan eliminations method, okay, so the purpose of, we will make 1, 0, 0. And also we have the part of here. Okay, so we will try to do the Gauss-Jordan elimination method to make the C11 equal to 0, C22 equal to 0, also the C21 equal to 0, C12 equal to 0. But we need to do this with the full pivoting. Full pivoting. Okay. And what is the full pivoting? When we try to make the C11 equal to 0, equal to 1. And for the full matrix, for the square matrix, usually we say that's the diagonal elements. Okay, however, since right now the C matrix is not a square matrix, so the C11 should be changed to maximum absolute. Of the entire matrix. Okay, so it means if we do the full pivoting for the C matrix, before we try to make the C11 equal to 1, we need to search for the entire C matrix. Then we need to find all the find the maximum absolute in all C matrix, in the entire C matrix. And for example, in the C matrix, if we got the Cij, which is the maximum absolute, then we need to change the maximum absolute to the new C11, So first we need to swap the ith row with the first row. Okay, so we need to swap the two rows. Then we need to swap the jth column with the first column. Okay. But when we change the two columns, the variables in the U vector need to be swapped. Okay, so when we change the two columns, but we like to keep the original equations unchanged. If we change the coefficient matrix if we change the jth column to the first column, and then we will swap the original first column to the jth column, then the variables in the U vector, the U1 need to be changed by the Uj. Okay, so that's the full pivoting. After we search for the new C11, then we can divide in this case we can make C11 equal to 1. First we can divide the entire equation, the first entire equations, by the coefficients C11. Okay, so all the elements in the C matrix, the first row need to be divided by C11. Also, the right-hand side vector need to be divided by C11. But since the right-hand side vectors, they are all equal to zeros, so it will make no difference. So okay, so we will then we need to do the procedure to make the C21 equal to zeros. Then right now we have 1. Okay, then we need to do the calculation. The 2 prime is equal to the 2 minus C21 times 1, first equation. Okay, so we need to, the second equation is minus C21 times first equation. In this procedure, we can make C21 becomes zeros. Okay, so that's the procedure. After this, it is 1, 0. Then we need to search the new C22. And we need to search all elements from the C22 to the C2n. Okay, so we need to search the the second row from C22 to the C2n. We need to search for the maximum absolute values, the new. Then we need to swap. For example, we have the C2L, which is the maximum. Then we need to swap the F volume. Okay, and also you need to swap the two variables. Okay, so remember, after we search, we need to swap. The earth column and the second column. But if you swap the two columns of the coefficient matrix, also you need to swap the variables in the U vector. Okay, so after you search the new C22, then the next stage we will make the C22 equal to the 1. Then the first equation minus C12 times the second equation to make C12 equal to 0. Okay, so that's the so-called the Gauss-Jordan elimination method. If we do the Gauss-Jordan elimination method, then we can make the C11 equal to 1, C12 equal to 0, C21 equal to 0, C22 equal to 1. Okay, so that's the so-called Gauss-Jordan elimination method. So in this case, we can make a partition so that's how do we make a partition. C and U. Okay, so you can say that's a unit matrix. There's a C bar matrix. So we have the U1 vector and the U2 vector. It is a 2 by 2. 2 by n minus 2. And for this one, 2 by 1. This one minus 2. Okay, so that's the partition of this one. Okay, so so far we if we follow the Gauss-Jordan elimination method, and remember we need to do the Gauss-Jordan elimination method with the full pivoting. Then we can always get a matrix like this one. And then you can say I times U1 plus C bar times U2 equal to 0, 0. Okay. Then we can swap the this one to the right. And then we will say the two elements in the U1 are called dependent variables. Okay, we will call the two variables in the U1 as the dependent variables, and the n minus 2 are independent. Okay, then we can call the variables in the U2 as the independent variables. So in these expressions, we can express the U1 can be expressed as functions of U2. Okay, so the U1 can be expressed as functions of the U2, as functions of the U2. Okay, after you got the relationship of this one, so you can say we can express two of the variables as functions of the other variables why I use the n variables, since you can express the C matrix by a 2 by 6 matrix, or you can express the C matrix by the 2 by 15 matrix. So I use a variable n. However, actually we need four other variables. We can get the relationship by the matrix, the C 2 by 6 matrix. So two of the six variables can be expressed as functions of the other four variables. Okay, so that's the purpose of this derivation. And also that's the second part of the homework. Okay, get the expressions for U1 okay, so it means that you need to do the Gauss-Jordan elimination method with the full pivoting, and to get the expressions like this one. Okay, so that's the second part of the homework you need to finish. Okay. Then what you need to do is the formulate the U vector by entire vector, it could be the 15 by 1 for the example problems. Since the totally we have the 15 variables for the example problems. Since we got 5 nodal points for the problems. So originally, totally we use 15 degrees of freedom for the U vector. And what is the U bar? That's the original entire global displacement vector. That's the displacement vector which include the displacement vector. Only the independent. Okay, so for the example problems, it will always be the 13 by 1. So since in the previous derivations, we know 2 of the variables, they can be picked out to be the dependent variables. Okay, so there are since we got the 2 constraint equations, so it means the 2 of the variables can be chosen as the dependent variables. Okay, the dependent variables can be expressed as functions of the other 4 variables, or they can be expressed by the other 13 variables. And how can we get this one? You need a matrix which is U bar equal to let's say the R vector, R matrix times let's see. Okay, let's say we need to have this one. This one is the original 15 by 1. This is 13 by 1. So it is a 15 by 13 matrix. So it is a 15 by 13 matrix. For example, in our previous example problems, node 1 is not affected by the 2 constraint equation. Okay, so you can say the U1 is equal to U1, V1 is equal to V1, theta 1 is equal to theta 1. Okay, so in the R matrix, the U1, V1, theta 1, they will be shown in the U vector. Also, they must be the first 3 elements in the U bar. So okay, since the U1, V1, and the theta 1, they will not be shown in the constraint equation. The constraint equations, they are related to the node 2, node 3, and the node 4. The first constraint equation is related to the node 2 and the node 3. The second constraint equation, it is related to the node 3 and the node 4. Node 1 and the node 5, they are not related to the 2 constraint equations. So the U1, V1, the theta 1, they will be the elements in the U vector. Also, the U1, V1, theta 1 will be the elements in the U bar vector. The same things can be applied to the node 5. So you have the U5, V5, and the theta 5 in the U vector. But also you have the U5, V5, and the theta 5 in the U bar vectors. And you just, since the U1 is the independent variables, so the original U1 vector just equal to the U1. It will be equal to the U1. But also it is true for the theta 2, theta 3, and the theta 4. Theta, the three rotation degrees of freedom, they are not related to the constraint equations. So you will have the theta 2, theta 3, and the theta 4 in the U vector. And these three elements, they will be shown in the U bar vector also, since for these 3 degrees of freedom, okay, so you have the okay, so there are 9 elements. There are 9 elements in the original U vector. They will be also shown in the U bar vector. So the transformation matrix, no need to do any change for this. So for the first 3, you can say only 1. And if we multiply the first row to the U bar vector, you will get an equation like this one. If you multiply the second row of the R matrix to the U bar vector, you will get an expression like this. Okay, so there are 9 equations, they will not be changed. And also, for the 6 elements, U2, V2, U3, V3, and U4, V4. In these 6 elements, 2 of these 6, they are dependent variables. But you still have the other 4 elements in these 6, they are independent variables. For the independent variables, you will get the rows in the R matrix in the same way like the first 3. Okay. Only the 2 variables, they are the dependent variables. You cannot find the corresponding elements in the U bar vector. Only the 2 dependent variables, they will not be shown in the U bar vector. So you need to use the previous derivations. We know the U1 is equal to negative C bar times U2 vector. You need to use that expressions to fill in the elements in for the 2 corresponding rows in the R matrix. Okay, so that's the part you need to finish for the third part of your homework. Okay, I'm afraid which is a little bit more complex for the students who learned first time to do this. But however, okay. So for the example problems, you need to find the R matrix. And so far I have not referred to how can we do the kinematic condensation. Since for the general constraint equations, you need to finish all these procedure to get the condensed stiffness matrix. So that's the previous preparations for the final step. In the final step, we can get the condensed stiffness matrix, and if you finish all this procedure, then you have finished the kinematic condensation. Okay, so I will stop the class, today's class here, and try to finish the homework. If you got any problems, you can send the email. I'm afraid sometimes I check the email not so frequently, so probably it will be a little bit late to respond. Okay, so.